I think it's the third video in chapter 8 where we're gonna start talking about oxidation of alcohols. I kind of said that these sections are mainly about preparation of alcohol, that is what we talked about last time. This section, today's video, technically is not preparation of alcohol, but using alcohol to make other things, like carboxylic acid. Okay. Now, that said, the key idea for oxidation of alcohols, I want you to know there's going to be the harsh reagent version and then the mild reagent version that result in a very different result. So that's what I want you to pay attention to. Okay. For the harsh reagent, basically the only example we're going to think about is chromic acid, with the caveat that you can actually make chromic acid in situ, meaning in the reaction flask within the reaction vessel you're doing the organic reaction in, from sodium dichromate and sulfuric acid, and that's usually how it's made, because this is so reactive that you can't really buy it, and so you have to make it yourself in the lab, like so. So sometimes the reagents are written like this, but what's actually being used is chromic acid, H2CrO4. Okay, so with that caveat, let's get into this. So with harsh reagents, you can actually take a primary alcohol and oxidize it all the way to carboxylic acid. And I say all the way because if you recall a discussion about redox, right? From alcohol, of course, the most oxidized would be the carbon dioxide, but that we're not gonna touch a reaction like that for now. Maybe a little bit later. But halfway oxidized would be aldehyde. All the way would be carboxylic acid. So that's what we're talking about. Okay. So harsh reagents can take you to carboxylic acid. If you have a secondary alcohol, I want you to notice that the carbon with the alcohol only has one hydrogen on it. So it really one phase of oxidation is all that's possible, and so for that reason you're going to get a ketone product. And that's it. Okay, there's no hydrogen you could remove at that carbon. So, okay, so here's an example. If you had this primary alcohol, right, the product is going to be this carboxylic acid. Notice the loss of these two hydrogens. But the mechanism, of course, is the hard part, and this is probably the most involved mechanism you've seen so far. Okay, and it's so involved that the first few steps we're not going to be able to cover it within this chapter because you kind of need the knowledge from the next chapter. But what I want you to notice is we're going to cover that in the next chapter, and so for that reason, after chapter 9 is covered, I'll assume that you'll be able to draw the step-by-step mechanism, the complete mechanism for this step. And so for that reason, on the exam, I might ask a mechanism for a reaction like this, which will be after both chapter 8 and 9 will be covered. And so for that reason, I want you to be able to write the complete mechanism for reactions like this. I hope that makes sense. Okay. So the first few steps are the steps that we're going to actually kind of skip for now. We're just going to call it the sort of magic chromate ester formation mechanism. And in chapter 9, we'll extensively discuss the ester formation mechanism. So I want you to take a look at that. For now, what I want you to know is that we're gonna see a condensation reaction. A condensation reaction just means like two things come together and spits out water. Okay, so this becomes water. Okay, and the two gets combined to become a chromate ester molecule. It's just like the ester functional group, regular ester functional group, in that you have something with chromium oxygen double bond and oxygen, and then an R group. Okay, this is a maybe I should not point to this. I should point to this. This is a chromate ester, as opposed to carboxylic ester. Okay. All right. Now, once we get to this step, and again, eventually I want you to be able to write out the entire mechanism after chapter 9. There's a proton here that water could take off. Now, you might wonder, why would water, a very weak base, would be able to take that proton? And that's because this chromium is pulling electrons. And the driving force for that, I want you to think about that with me. This chromium, can you calculate the oxidation state from the perspective of chromium? It's bonded to a more electronegative atom, oxygen, 6 times over, so this is +6. And so it's very much oxidized, meaning it's very much electron deficient. And so for that reason, it's really just dying to take these electrons to itself, like so. Okay. So the chromium can get reduced a little bit. Okay. And so for that reason, right, like, but if that happens, right, oxygen is going to be very electron deficient. It just has these lone pairs. So the oxygen will need these electrons. So something has to take this proton off as a base. And that's why even a weak base like water can do this, because there's a strong pull of electrons toward chromium. And this is the key step in this whole mechanism. And I want you to notice this is indeed a oxidation step, which is kind of like E2 in that this is your leaving group, and then base is pulling a proton to form a double bond. Okay, now that will leave us with, right, this aldehyde. But remember, that's only halfway through the mechanism. And then if you're wondering what happens to the chromium, it would look like so, which is got the oxidation state out of now +5. So I want you to notice from the chromium's perspective, it got reduced and not carbon got oxidized. By the way, this is called chromous acid. It has one less oxygen. Now, what happens with aldehyde is that this could pick up a proton because it's in a very acidic water like this. I want you to notice this water picked up a proton to become hydronium ion. Right? So once that happens, you get that. Now that would make this carbon very partially positive, very electrophilic, and so now a weak nucleophile like water can attack it. And of course, otherwise this carbon would have too many electrons, so the electrons get kicked up to the oxygen. Right, this is a very electrophilic species. And this process, we would call it hydration of the aldehyde, because, well, it got hydrated. It was a water molecule was added, right? So okay. At this step, you got I should have given myself more space here, sorry. You got an alcohol again, kind of. It's actually called a hydrate because you got two OHs on the same carbon, but notice we basically have another alcohol group again, and so after loss of proton, this extra proton, this could undergo another chromate ester formation again. And again, for the actual mechanism, perhaps on the exam, I want you to draw out the whole mechanism. Again, we're just going to talk about this ester formation in the next chapter. But once you go through that, right, perhaps with the chromous acid, and again, we're going to lose a proton in OH group, so you get this chromous ester, one less oxygen. Now, one thing I want you to notice is at this carbon that's getting oxidized, you still have a proton, and so the same thing happens that we saw earlier, which is that chromium still wants to very much get reduced, so it pulls electrons, and so for that reason, even a weak base can pull this a proton, which is kind of like an E2 reaction, but technically not, because E2 reaction involves a strong base, not a weak base like this. But nevertheless, what that gives you, I want you to notice, is this carbon-oxygen double bond. So you get the carboxylic acid product, and then chromium now gets to become this species that it is only a +4 oxidation state, so it got pretty much very much reduced. Okay. So the sort of the takeaway of this is oxidation happened twice. And that's because the aldehyde got hydrated. With this setup, right? And so here's a key intermediate. The hydrated aldehyde contains a functional group that's like alcohol again, and that's why the second oxidation step can happen. Now we're going to go over perhaps these two reaction examples during class, but you could think of it as a homework. What would be the product here? I want you to think about it. Okay. Now let's contrast that to the mild reagent situation. An example of this is going to be pyridinium chlorochromate. Now, excuse me, there's other examples kind of like this, but for our class, that's probably the only one that you would see right now. But other examples include you might encounter, it's called Swaran oxidation, or Swaran reagents, or Dismartin periodinate. Okay, so those are some examples that you might come across. This is often just abbreviated DMP. I said pyridinate, but it should be pyridinane. Sorry about that. Okay, but they do the same thing as PCC, or pyridinium chlorochromate. And this is what the PCC looks like. Pyridinium is because pyridine is this ring, but it's got a proton on it to become a cation. Remember, the cations end with -ium ion, and anions end with -ate or -ide ion. So here's your chlorochromate. It's a salt. Okay. Notice that in this example, we're using a primary alcohol, and the product, if this was a harsh reagent, right, you should have ended up with a carboxylic acid, but this ends up giving you an aldehyde product. Okay, that's the difference between harsh and mild. So how does this happen? The first thing, these two are going to condense just like earlier. Now, what happens is that unlike earlier where we saw the condensation and loss of water, okay, here we're gonna see the loss of HCl. Okay, so I'm gonna maybe do. So this is gonna be HCl loss or condensation. Okay. Besides that, we could say that the chromate could pick up the proton to reveal pyridine. So I'm kind of doing two different things at the same time just to save space. Here's another condensation again. Again, see chapter 9. So if you're pretty sharp, right, like you should notice that's the exact same intermediate that we had earlier. So you might ask, well, what's the difference? Well, we'll get to that in a sec. The pyridine is a fairly basic amine compound. If you use it, you want to be careful. It's kind of somewhat carcinogenic, but also makes men sterile. So that if you're a guy, work with pyridine, you want to be careful, okay, for your future family and such. But pyridine can act as a base to pull that proton off. Remember, that's sort of the oxidation step. It's kind of like an E2 reaction. And then, of course, you get to the same aldehyde. Now, you might say, well, gee, we're not learning anything new here. What's the difference? And then you also get the exact same chromous acid. So what's the difference? Well, I want you to notice in this reaction mixture, there's no water present. And earlier we didn't quite say this, but typically the solvent that's used here is water. And so in this harsh reagent condition, there's going to be enough water molecule around to participate. But I want you to notice in this case, we only condensed and spit it out HCl. We didn't even spit out an extra water molecule. So there is no water molecule anywhere at all to be able to hydrate this. Okay, so that's the difference. Maybe we'll say reaction stops here. Okay. Hope that makes sense. And so for this reaction, it's really important to keep everything anhydrous, meaning like you have a glassware and everything that's free of water and whatnot, and otherwise you won't end up with this aldehyde product. And once again, like as before, we'll compare notes on the answers to these example questions here. So please do these, and then let's meet during class and compare the notes. All right, see you then.